So for this problem, it says here that we have a horizontal rigid bar with a length of 2r and its pivot is at its center. Now the bar is free to rotate through this vertical axis. And from the problem, it says here that there is a point particle of mass m attached to this bar. And at the other end is a container which is also attached to the bar itself. Initially, there is a point particle moving at a velocity of v, which is linear velocity, and the mass of the point particle, represented by this white circle, is equal to m over 3. Now, after some time, this particle collides with the container and gets stuck. Now, after collision, well, obviously it's inelastic collision because these masses together get stuck. The system starts to rotate through the vertical axis. Now, what are the things that we have to neglect? From the problem, it says here that we can ignore the mass of the rod and the mass of the black container here. Now, what's the first question from the problem? Well, it says here that we have to write an expression in terms of m, v, and r for the angular of the system before collision. So in other words, what is its angular momentum before colliding with the particle here? Now we know that angular momentum is denoted by L is equal to I omega squared, where I is your moment of inertia, and omega, rather, not squared, is known as the angular speed. Now, since this is a horizontal rigid bar, we will be using its moment of inertia as 1 over 12 ml squared, because initially there is no collision. Therefore, we are assuming that this is one system. Thus, we are using 1 over 12 as we will be able to check from our previous notes that the moment of inertia of a rigid bar is equal to this. Now, we know that your L here is equal to 2R. So therefore, we will also represent L is equal to 2R. Now, following the formula, L is equal to I omega, L is equal to 1 over 12 ml squared. We substitute 2R to L squared, thus becomes 2R squared times omega. Simplifying, this gives us L is equal to m over 12 times 4r squared omega. Now, what is omega? From our previous discussions before, we know that omega can be obtained from the formula V. V is equal to 2r omega, which is the relationship between your linear velocity, which is v, and its angular speed or angular velocity, which is omega. Now, after that, once we substitute v over r with omega, we can now simplify and we can obtain L is equal to mvr over 3, which is similar to the marked scheme. Now, let's move on to the second question. But please take note of every quantity that we will be obtaining. Now, let's move on to what is asked for the second question. Now, the second question is asking you to calculate what will be the angular momentum after colliding. And you have to prove and to show that the angular momentum is equal to 4/3 mr squared omega. Now, using the main formula, L is equal to I omega, we will be able to prove how are we going to get a final angular momentum of 4/3 mr squared omega. Now, going back, we can now get I, your moment of inertia, actually as mr squared plus m over 3r squared. What does that mean? It means to say that we are now going back. Since from the problem, the point particle m over 3 got stuck from the other end of this rod, therefore, we will now get the summation of the moment of inertia. We will not be using 1 over 12 anymore. Why? This is because we have now specific masses attached to each rod. from the left side we have m, from the right side we have m over 3. So therefore we get the moment of inertia of this mass and the moment of this inertia of this mass here relative to the pivot point, which is at the center. Going back, that means to say that our expression for the moment of inertia after collision is mr squared plus m over 3r squared. Now, after adding this together, this gives you 3mr squared plus mr squared over 3. This results to L, which is your angular momentum after collision, is equal to 4mr squared over 3 omega. Thus, we were able to prove the angular momentum after colliding. Now, we now go to the third question. So it says here that we have to prove that your omega, or your angular speed, is now equal to v over 4r. Well, we already know that the main formula actually, the general formula for us to get v with respect to omega is v is equal to r omega. However, since in this system we are using different masses, we just have to prove that using before collision and after collision, we will be able to obtain omega is equal to v over 4r. In order for us to do that, we will be using the conservation of momentum, which states that the angular momentum before must be equal to the angular momentum after. Now, from our previous calculations, we were able to get that the angular momentum before collision is m over 3 v times r, and after collision, the momentum becomes 4mr squared over 3 omega. After that, the best way for us to approach this problem is to eliminate all the fractions or to convert the fractions to whole numbers. So, relatively speaking, since there is an equal sign, we can just multiply everything with 3. Therefore, if we multiply all the quantities in the parentheses, the denominator will be cancelled out, becomes mvr is equal to 4mr squared omega. We are looking again for omega, therefore, if we divide both sides with 4mr squared, this gives us omega is equal to mvr 4mr squared. Canceling out like terms, r and r squared are like terms, m and m are like terms. Therefore, we arrive with the conclusion that your omega is equal to v over 4r. In other words, the linear velocity of this system is actually equal, can be denoted with the expression omega, which is the angular speed, is equal to v over 4r. Now, we will be setting this aside because we will be using this expression later on. Now, moving on. From the problem, it says to you that we have to get the energy lost. So, in other words, what is the change in kinetic energy? For us to get that change in kinetic energy, we go to our first unit formula, which states that we have to find the difference between final kinetic energy minus initial kinetic energy. Now, initially, kinetic energy before collision, it's 1/2 mv squared. Why? Because initially, before the point particle is moving linearly before colliding. It has one dimension. Therefore, using 1/2 mv squared, we just replace m here with m over 3, which is the mass of the point particle. Thus, simplifying, this gives us mv squared over 6. Now, this is the kinetic energy initially. Now, what will be the final kinetic energy? Well, the final kinetic energy, we know that this initial kinetic energy, the linear motion or translational motion will become rotational because from the problem it says that after colliding, the bar will actually rotate. Therefore, we use the kinetic energy formula for rotational motion, which is 1/2 I omega squared. Now, substituting the values that we have obtained before, we know that your I is actually the combination of moment of inertia for the mass of the end of the rod plus the point particle times omega. Now, simplifying, this gives us 1/2 4mr squared over 3 omega squared. Now, previously we have proven that your omega is equal to V over 4R. Therefore, we will be replacing your omega squared here with V over 4R. Thus, finally, we can say that 1/2 times this expression. We will just be simplifying further. Thus, this gives us this expression here. Now, we cancel like terms. 4 and 16 are like terms. Therefore, we will end up with mv squared over 24. Now, we can't stop yet because we want to get the change in kinetic energy. Therefore, we have to find the difference between your final, which is mv squared over 24 minus the initial, which is this. Simplifying, this gives us 3mv squared over 24, or simplified version is mv squared over 8. So in other words, this is the energy loss during the collision. Alright, to continue, we go to the next problem. It says here that what if we have a torque of 0.010 Newton meter, which brings the entire system to rest after colliding after a number of revolutions. So these are the conditions. We have R, M, and V values. Now, what you have to find is you have to show that the angular deceleration of the system is 0.043, which makes sense that there must be angular deceleration because we want to bring the system to rest. Therefore, it must slow down. Thus, using the formula torque is equal to I alpha, we can derive a formula for our angular deceleration, which is alpha is equal to tau over I. Now, we know that your tau over I, we already know that your I is a combination of the moment of inertia of the mass plus the point particle. Therefore, simplifying, this gives us alpha is equal to tau over 4mr squared over 3. Now, in mathematics, this becomes an inverse. When you divide tau with a fraction, this becomes an inverse, thus becomes 3 over 4 times tau over mr squared. Now, substituting the values here, we have torque, which is 0.010. We have mass given and R given. Thus, our deceleration is 0.04286 or 0.043 rads per second squared. Alright, moving to the last problem. It says here that we have to calculate the number of revolutions made by the system before coming to rest. When we talk about revolution, we're actually talking about angular displacement or how much did it cover. Now, using the formula for uniform rotational acceleration, which is final angular speed squared is equal to initial angular speed squared plus 2 alpha theta, we can now derive a formula for your angular displacement, which is theta. This gives us omega final squared minus omega initial squared over 2 alpha. Since it comes to rest, your omega final squared will become 0. This will leave us this expression, which is negative omega I squared over 2 alpha is equal to theta. We know previously that your omega is actually equal to V over 4R. Thus, we substitute the values here in the numerator, becomes negative V over 4R squared over 2 alpha. Simplifying, this gives us V squared over 16R over 2 alpha is equal to theta. As we know, we get the inverse since this is a fraction. Thus, we can finally say that V squared over 32R alpha is equal to theta. Now, substituting the given values, your V is given, which is 2.1. We have R also, which is given, 0.5. This, by the way, is squared, sorry. And your alpha or angular acceleration is this. Now, simplifying everything, this gives us a theta of 12.8 radians. However, we can stop yet because we're going to talk about revolutions. You are asked to find revolutions. We know that one revolution is actually 2 pi rad. So in other words, one complete revolution for a rotational motion or circle is equal to 2 pi. Therefore, we have to divide your 12.8 with 2 pi. And finally, this gives you an answer of 2.0 revolutions. So that's it.